1 second. It's not popping up with the thing I want to share. Okay. All right. So, hi. As Ben
Do,
introduced.
do you know you have the presenter view on like half of your screen? No, that made it worse.
Okay, 1 second. It's only giving me the option to share the presenter stuff, not the actual presentation itself.
I believe you can do it without notes.
Okay.
There you go.
All right. Awesome. So, hello. My name's Abigail Harrison, as Ben introduced me. This will be a presentation on risk limiting audits and a new proposed method to conduct them created by myself, Benjamin Fuller, and Alexander Russell. As I'm going through this presentation, if you have questions at any time or are confused, please feel free to interrupt me. Or I guess in this case, Ben will have to unmute you so you can talk or send a message in the chat. So just a brief overview of what this presentation will cover. First, I'll start with an introduction to risk limiting audits, or RLAs. Then I will discuss normal ballot comparison audits, which are key to understanding our new proposed method. Then I'll cover the current state of Connecticut audits and finish up with explaining lazy comparison RLAs, which is the modified version of comparison RLAs that we came up with. So first, what is an RLA? The goal is to verify the outcome of an election by re-examining cast ballots. This procedure should detect tabulation and aggregation failures that affect the outcome of the election. Or in other words, it should find a bad election. By bad election, I mean that the election results did not portray the correct winner and loser. I would like to note here that risk-limiting audits do not attempt to detect a difference in vote totals, only the difference in the outcome. The procedure involves selecting a random sample of ballots, so there is a thing known as risk. The random sample of ballots here increases as margin of victory decreases. A smaller margin of victory means a greater chance of error in the audit, so you need to look at more ballots in order to ensure you find the correct election outcome in the audit. At especially small margins, such as 0.5%, many states just choose to hand recount instead of conducting an audit. So I mentioned the risk. The risk here is the chance that a bad election will not be detected by the audit. Risk limiting means there's an explicit bound on this risk. Risk limiting is how we achieve the statistical guarantee that an RLA provides. So for example, a 5% risk limit means there's a 95% guarantee that you will find an issue with the election results, if there is one. There are three main risk limiting audit methods. The first is hand recount, or looking at every single ballot. This has a 100% statistical guarantee of finding an issue with election results. The second is ballot polling, and the third is ballot comparison, both of which I'll cover in a later slide. I would like to note that there are two types of comparison audits. There's ballot and batch comparison. This presentation will focus on ballot comparison, but keep in mind that everything I say about ballot comparison can apply to batch comparison. You simply examine a batch or a grouping of ballots rather than a single ballot as you do in ballot comparison. So, there are a few requirements in order to conduct a risk limiting audit. The first are paper ballots. These are important because they're immutable records of voter intent, and they're examined during the audit procedure. There's a ballot manifest, which is a document that lists each batch and the number of ballots per batch. This should be created by hand and not by a machine. A batch is a grouping of ballots, and this group must stay consistent throughout the entire audit. Then there's tabulation totals. These are necessary in order to compare the election results to the audited results. And finally, a cast vote record, or CVR. This is a list of every ballot, its identifier, and its votes. It's key for ballot comparison audits. So I've included a picture of a CVR here as an example. As you can see, the top row here is the contest name. For simplicity purposes, we just used incrementing contest numbers. So you see contest 1, contest 2, etc. And the vote for equals 1 means that voters can only vote for one candidate in this contest. Underneath that is the candidates' names. And then after that is all the ballots. The imprinted ID row you see here is the ballot identifier, and the ones and zeros stand for votes, 1 being a vote, 0 being not a vote. So now I'll briefly cover ballot polling RLAs. To start, the auditor pulls a random sample of n ballots. The number of ballots they pull depends on the margin of victory. Then they tally the votes for each candidate on these ballots. If the winning candidate for these ballots matches the tabulated winner, then they declare that the election results seem correct. Otherwise, they must examine another sample of ballots, known as a round, or conduct a full hand recount. For ballot polling, at small margins, you have to poll an extremely large number of ballots. For example, at a 1% margin of victory, Connecticut would have to examine 60,000 of its ballots if it did a ballot polling audit. However, the nice thing about ballot polling RLAs is there's no setup other than just the ballot manifest. The work in ballot polling RLAs comes entirely with the number of ballots you have to poll. Have any questions?
Maybe just since it's hard for people to ask, why should you expect the winner of the random sample to be the same as the winner of the actual, or sorry, why would you expect this to work?
Okay. So essentially, you're looking at a large sample of ballots. And as long as the sample is random, you expect the results of this sample to match the results of the tabulation. So for example, if the winner won by a margin of 20%, then there should be 20% more votes for the winner than the loser in this random sample. Okay, so now I will cover ballot comparison RLAs. There are two main parties in ballot comparison RLAs, the trusted auditor and the untrusted party, or as you may know it as, the adversary. So in this case, trusted is someone we know will conduct this audit properly. They have no malicious intent. They want the audit to complete successfully, and there's no reason to question the source's integrity. They will be requesting things from the untrusted party, represented by the world here. They have unknown intent, so we can't be sure if the data that the auditor requests of them is real or fake. In real life, this reflects all the external parts of an election and its audit, such as the tabulators used, their possible misprogramming or misuse, possible like data misentry, etc. It could also be someone with malicious intent, and in that case, their goal is to give the appearance that they're cooperating with the auditor's requests in order to say it's a successful audit while trying to thwart the audit every step of the way. The goal is to verify the election results, even with the data coming from this untrusted party. So there are two parts to the setup. First, the auditor receives the ballot manifest from a trusted source, such as if they were to make it themselves. The untrusted party receives physical, untampered ballots. I'd like to note that the untrusted party cannot produce new ballots, change the contents of these ballots, or do anything to these ballots at all. They represent an immutable physical record. So now for the procedure. The auditor first receives the tabulation totals from the untrusted party. For example, the untrusted party in this case could just be the tabulator itself. It's an external part of the election audit and therefore it's untrusted. The auditor then sends a request for the cast vote record, or CVR, to the untrusted party. And before the party can respond with the CVR, it must assign ballot identifiers to every ballot. So this here is an example of a ballot with an identifying QR sticker on the back. As you can see at the bottom here, the identifier is 105. So this is just to give you insight as to what an identifier could look like. So moving on, after assigning ballot identifiers, the party gives the auditor the CVR. The auditor can now perform a series of checks on this CVR, which are necessary because it came from an untrusted source. It should compare the winner on the CVR to the winner on the tabulation totals and ensure that they match. This is the sole purpose of receiving these tabulation totals, otherwise they're ignored. The auditor can also compare the batch sizes between the ballot manifest and CVR, as the CVR should list every batch the ballot is a part of. The auditor should also check that every identifier on the CVR is unique, as the interested party was the one to assign them. However, I want to stress that in these audits, there's no specified action to take if any of these checks fail. It's kind of up to the auditor and audit administrator's discretion as to what action to take, and there are no clear instructions as to how to remedy any of these mismatches or errors. So now that the auditor has the CVR and performed these checks, they can start requesting ballots to audit. The auditor should request a specific physical ballot from the untrusted party through its identifier, I. In the case of the ballot I showed you, I would be 105, or whatever it's listed on the CVR as. As I said in the previous slide, it's possible for this untrusted party to be malicious and uncooperative. For example, they may just outright deny to respond with the requested ballot. In the event that the interested party were to do this, as well as mess with other aspects of the audit procedure, such as giving a bad CVR, then the default response would be to stop this audit and simply go do a full hand recount instead. Since the untrusted party is not allowed to mess with the physical ballots themselves, looking at every ballot would accomplish the same thing as a comparison audit, just with a lot more work. For the sake of this explanation, we'll assume that the untrusted party responds with ballots when requested. So it responds with the requested ballot. Once the auditor receives this ballot, the first thing they should check is that the identifier on this ballot matches the one they requested. This may seem obvious, but it's important to make sure that the untrusted party gave them the correct ballot, and if they did not, they should request the ballot again until they receive the correct one. Once it has the correct ballot, they interpret the ballot's votes to the best of their ability, and they compare their interpretation of these votes to the votes marked down on the CVR they received. So the two parties repeat this process. The auditor requests the ballot, the untrusted party responds with the ballot, the auditor verifies they received the correct ballot, and then compares it to the CVR. This process can be simultaneous, as multiple auditors can be requesting and interpreting different ballots at the same time. They continue doing this until the end of the audit. So after looking at a certain number of ballots, which is more if the margin is smaller, the auditor can either declare the audit as complete or inconclusive. If the audit is inconclusive, they will have to look at more ballots, also known as another round, until either they can declare the audit as complete or they decide to conduct a full hand recount instead. So are there any questions about this?
Does anybody want me to unmute them or raise whatever I have to do? I don't see a hand. I think you're okay, so keep going.
Okay. So I keep emphasizing that the number of ballots you have to examine is larger as the margin gets smaller. And I think it would be helpful to show a visual for this, especially for the difference between ballot polling and ballot comparison. So these graphs that I'm about to show you use data from the 2020 Connecticut election, and the number of registered voters is around 1.8 million. They utilize a 5% risk limit, which again means a 95% statistical guarantee that an issue with the election outcome is found. So first off, this is the graph for the average number of ballots in a ballot polling audit. As I said when I talked about ballot polling risk limiting audits, a 1% margin means that over 60,000 ballots are examined, as you can see here in this graph. It decreases very quickly, and the number of ballots needed at a 5% margin goes down to about 2,500. At a 25% margin, all the way at the end there, the number of ballots decreases to below 100. They do not require a lot of setup. As I said, they only need a ballot manifest. However, at small margins, you need to poll an insane number of ballots. This will be emphasized as you see the graph for ballot comparison, which I'm going to show you next. So just keep that 60,000 number in mind. So this is the graph for the average number of ballots polled in a ballot comparison audit. Here, a 1% margin means that 750 ballots are examined, which is a lot less than that 60,000 I just showed you. At 5%, the number of ballots gets close to about 100, compared to 2,500 for ballot polling. This makes ballot comparison seem a lot more appealing, especially at small margins. However, the setup cost is much higher. You need to generate a CVR in order to conduct a ballot comparison audit. This requires scanning individual ballots, ensuring identifiers are unique on the CVR, and a slew of other checks. The dominant cost in ballot comparison is CVR generation, but it comes with the benefit of examining a lot less ballots. So, a few other aspects of risk limiting audits. The first one is ballot identification, which you saw in the procedure is necessary so you can request a ballot with identifier I. It's starred here because it's not 100% necessary. However, not having an identifier when a specific ballot is requested can cause huge discrepancies when it comes to examining these ballots. It generally means it's harder to pull the correct ballot the first time, and there's also no way to ensure you receive the correct specific ballot that you want. Then there's ballot storage. This is pretty important, especially when it comes to creating and storing batches. There's an interesting trade-off here with batch size and storage. So large batches, and again, batches here means a grouping of ballots, means less storage, but it's also harder to pull a specific ballot from a large batch. Small batches mean you need more storage, but it's easier to pull a specific ballot. I've attached some pictures of ballot storage devices here. On the left, this is a portable ballot storage bag, and on the right is a popular storage bin known as the DS200 ballot bin. If you store one batch per bin and have super small batches, you can see how the size of the room you need to store these bins can get very large. Finally, there's software. There's currently some software on the market, but since RLAs are newly implemented, there's not many choices for it. So now what Connecticut does. Currently, Connecticut audits have you randomly select 5% of the precincts to participate in an equipment audit. An equipment audit does not attempt to verify election results, just that the equipment used in the election is operated properly. Precincts who are chosen have the choice of using either the audit station, which is a machine that scans and tabulates ballots and is not used in the election, or of doing a full hand recount. Most of the precincts just choose to recount. These audits are not risk limiting. Though the methods used are risk limiting, such as hand counting, only examining ballots from 5% of precincts does not cover enough of the ballots to have a high probability of finding an error. It does not provide statistical guarantees at smaller margins because of this. Other reasons they are not risk limiting is that the work does not scale with the margin. As you just saw in those graphs, the number of ballots you have to examine in a risk limiting audit scales with the margin of victory. In our audits, we look at 5% of the precincts regardless of how close or far the margin is. Although there are no clear instructions for comparison RLAs and how to handle certain discrepancies, the general guideline is that the more discrepancies between the ballot and CVR, the more ballots you pull to check. For Connecticut audits, there are no instructions such as this. And then something interesting to note is that our audits do not have what we call the force of law. If the audit goes poorly, as in we find a lot of issues in the election when we conduct the audit, this does not invalidate election results. There is also not a point where we declare that the audit has shown too many issues and we must conduct a full hand recount to verify results. So there are a few hurdles to adopting risk limiting audits in Connecticut, which I'll now cover. We have a couple unique state features. So first off, we have town managed elections, which means that each town has their own election and carries their own ballots. This makes ballot polling difficult because selecting a random sample of ballots means having to poll and tally ballots from all across the state rather than at a single location as a lot of states have. We also do separate precinct tabulation, which is actually kind of a good thing because it allows for automated batch sizes. We can simply make one precinct a batch when they tabulate it. We also use the audit station, which as mentioned in a previous slide is a machine that is capable of scanning and tallying ballots, and it's not used in the election. And then we have a lack of ballot identifiers. As mentioned earlier, ballot identifiers make polling a specific ballot a lot easier. Connecticut ballots do not have any identifying marks on them, which makes conducting risk-limiting audits difficult. Placing identifiers on a ballot is also a very delicate situation. There are privacy and security trade-offs depending on how it's done. If ballot identifiers are printed on the ballot before ballots are cast, as in the voter can see this identifier, then a voter could display their ballot with the identifier and confirm they voted in a specific way. This may not seem like a big deal, but there could be implications of vote selling with this setup. If they are added after the ballots are cast, then we have to print onto a ballot, which could lead to markings in areas that could affect ballot interpretation during the audit. So there's not really a clear, easy solution for this type of hurdle in Connecticut. Finally, CVR production is costly because there are no CVR producing tabulators in Connecticut. So the current status of RLAs in Connecticut is that a Senate bill was created but not voted on in the regular session. So now I will cover lazy risk limiting audits, which is the method proposed by Benjamin Fuller, Alexander Russell, and myself. Sorry, one second. So the goal of lazy risk limiting audits is to reduce the cost of CVR generation in comparison audits. We made this our goal because in states without CVR producing tabulators, CVR generation is the predominant cost in comparison audits. While ballot comparison is more appealing at smaller margins, the CVR cost overshadows the cost of polling ballots if you were to do ballot polling at larger margins. The difference from normal ballot comparison audits is that CVRs are only generated for batches from which the ballot samples are drawn. Again, a batch is a collection of ballots that are tabulated together. And part of Connecticut is the fact that we do ballot tabulation by precinct, so we almost have batches set up already. The conclusion we have is that it improves efficiency in distributed elections without CVR producing tabulators. For example, at a 5% risk limit and a 5% margin of victory, we found you only need to generate roughly 14% of the statewide CVR. This equates to 14% of the cost of producing a CVR in the first place, thus reducing the overall cost of conducting comparison RLAs. So now for lazy comparison RLA procedure. They receive the same items. The trusted auditor and untrusted party receive the same items that they received in the normal comparison audit. So the trusted auditor receives the ballot manifest from a trusted source, and the untrusted party receives untampered physical ballots. The way our proposed lazy method differs from normal comparison is in the procedure, as you'll see. Once again, I stress that the ballot manifest comes from a trusted source, so we don't have to question its integrity, and the untrusted party is not allowed to mess with the physical ballots in any way. So the start of the audit. Once again, it starts with the auditor receiving tabulation totals. Again, the untrusted party giving these could just be the tabulator themselves. The auditor then begins by selecting a batch size and requesting a CVR for this batch. The batch is chosen at random. So they request the CVR, and before the untrusted party can respond to this request, they must assign ballot identifiers to every ballot within the batch. So once they assign the identifiers, they can respond with the CVR. Like in the case of normal ballot comparison, the auditor can now perform a series of checks on the CVR, which are necessary because it came from an untrusted source. They should compare that the winner of the CVR and the winner for the tabulation totals match, ensure batch sizes match across all documents, the ballot manifest, the CVR, etc., and that each ballot identifier on the CVR is unique. These are just the same checks that they had to do for normal ballot comparison. However, we propose solutions for how to handle these mismatches, which I will address in a later slide. So now that the auditor has the batch CVR and performed these checks, they can start requesting ballots. Again, they should request these ballots with the ballot identifier. So once again, I want to say that the untrusted party could be completely uncooperative and refuse to respond with ballots, for the sake of this explanation, we will assume that they respond with the requested ballot. So, once this auditor receives the ballot, they should check the identifier to ensure they have the correct ballot, and once they do that, they can interpret the ballot's vote. They should interpret it to the best of their ability and compare their interpretation to what it says on the CVR. The two parties repeat this process. The auditor selects a batch and requests a CVR for the batch. The untrusted party responds with the CVR. The auditor requests a specific ballot. The untrusted party responds with the ballot, and they repeat. Sorry. After looking at a certain number of ballots, the auditor can either declare the audit as complete or inconclusive. If inconclusive, they'll have to look at more ballots, which is another round, until either they can declare the audit as complete or they choose to full hand recount instead. So as you can see, this is very similar to the normal ballot comparison procedure. The main difference is the fact that instead of requesting and receiving one CVR at the beginning, the auditor requests a CVR per batch. Are there any questions?
I'll just say while you're paused, you mentioned this in normal ballot comparison, but it's true here. You can run these in parallel. So you could tell 100 towns, hey, give me a CVR for this batch and wait, right, and yeah.
Okay. I think we're good, so I'm going to keep going. So now I will cover the auditor's role in detail. In our paper, we define three main functions for the auditor: audit, basic experiment, and check consistent. The audit function is to just perform basic experiment until the stopping time, such as enough ballots have been examined in the round. The function audit either outputs consistent or inconclusive, depending on discrepancy results of basic experiment. So now I'll cover basic experiment and the discrepancy results. So first, basic experiment is just that lazy comparison procedure I showed you. The auditor picks a batch, requests a CVR for the batch, and then picks a ballot at random from that batch. The auditor then transforms the CVR. These are the fixes to the checks on the CVR I said the auditor must make. I'll be getting to this soon. Then the check consistent function is run. If it returns an error, then the discrepancy is set to 2. So a note on the discrepancy here. Discrepancy can be 2, 1, 0, -1, or -2. A discrepancy of 2 here means, for example, the CVR showed a vote for the winner, but the ballot showed a vote for the loser. Since 2 is the highest discrepancy, we call this our worst case scenario. So if the check consistent function returns an error, we simply default to our worst case scenario for the discrepancy. If it does not return an error, then we set the discrepancy to the difference between the winner and loser votes between the CVR vote for that ballot and the actual ballot, as you see here. W stands for the winner, L stands for the loser, CVR stands for the ballot on the CVR, and ACT stands for the actual ballot itself. So observed discrepancy. The overall observed discrepancy for the batch is this function you see at the top here. It's very similar to the function we saw in the previous slide. So it's the difference between the tabulated winner and loser votes minus the actual winner and loser votes for the batch, divided by all the votes in the batch, denote which is S here. An example expected discrepancy would be like so. In the tabulated votes, Biden received 500 and Trump received 1,500. But in the actual votes, Biden received 1,400 and Trump received 600. This would result in an expected discrepancy of -0.9. I'd like to note that the difference between the equation in the previous slide and the equation in this slide, first off, is the fact you divide it by the batch, which is because this is the overall discrepancy, but also the fact that you compare the tabulated votes to the actual votes instead of the CVR votes to the actual votes. This is to show you that as long as we have the tabulated votes and CVR votes, using the equation from the previous slide, we can sample discrepancy. This is also to show the importance that the CVR results remain consistent with the tabulation results. We perform checks and transform the CVR to ensure this is the case. This makes sure that we handle the errors to make the CVR discrepancy consistent with the tabulation discrepancy. So that was kind of confusing. I'm just going to stop and just make sure there's no questions.
So, sorry, maybe just let me. So you're saying this is discrepancy for a batch. What's discrepancy for an election?
For an election, it would be the sum of all the discrepancies
Okay.
for every
And
batch.
and just to make sure, why does discrepancy matter? Why do I care about measuring
Okay.
discrepancy?
So discrepancy is essentially the difference between what the untrusted party gives you when the auditor requests stuff and what the actual circumstance of that data is. So it's essentially comparing the data you receive from the untrusted source to the actual data, real data itself.
Okay, and let me ask, so why do you care about measuring it?
Okay, you care about measuring it because that's how you determine if the election results match the audit results. So when you audit the ballots, you want to ensure that you get the correct outcome and it matches the election outcome. And you do so by noting the discrepancy between the audit results and the actual ballots themselves.
Okay, so let me say that a little bit more formal for the theorists that are on the call. Um, um, right, is um, sorry, the bounding discrepancy as being less than the margin of victory is sufficient to say that the election is good. So if you can bound the probability that discrepancy is bigger than the margin, you can bound the chance that the election is bad. So that's why we care about measuring discrepancy. Alex, I'm going to ask you to unmute yourself. Do you want to speak? I asked you, maybe. You have to accept my unmute request. So,
Did that work?
yes.
Oh, okay, great. I'm just curious. In terms of this observed discrepancy, so here we've got this big batch with all these ballots in it. Obviously, something has gone horribly wrong here, right? So the truth is that the balance of votes in this batch is by far in Biden's favor, but the tabulation is by far in Trump's favor. So okay, so given that the discrepancy here is this number, whatever it is, negative 0.9, what does that mean would happen if I drew a random row of the CVR and compared it against, the associated ballot? I mean, in a sense, you've already addressed this problem. Ben's question was, so what's the point of discrepancy? This is a similar question. I mean, so can you sort of explain what's the like where does the tire really meet the road here? So at some point, like we need to understand what's going to happen if there's a big discrepancy, if there's a big inconsistency in the election, and I pick a ballot. Um, yeah. So if there's a big inconsistency in the election, somehow we need to guarantee that I'm going to observe that if I pick a ballot. So what's going on here with this negative 0.9 discrepancy?
So when you pick an actual vote, you're more than likely to find from looking at the actual ballots that Biden is the winner over Trump. However, if you look at the tabulation results, it claims that Biden is the loser and Trump is the winner. Again, just to note, the tabulation results come from an untrusted source. So when you're looking at the actual ballots, you're looking to see that they match the untrusted data. When you get a discrepancy such as 0.9, it means that you're very likely to find that the data between the tabulation and the ballots themselves do not actually match. As I said, I gave an example earlier, a discrepancy of 2 means that a ballot for the CVR claimed the ballot was for a winner, but it was actually for a loser. With a discrepancy of negative 0.9, it again means that you're more likely to see a ballot that does not match the tabulation results.
Yeah, but let me just say, like, a negative discrepancy is actually okay because it means that the winner got more votes than was reported. So there's actually a bigger margin than we thought. So when you observe negative discrepancies, you don't necessarily say, I need to audit more. Right? When you observe positive discrepancies, you say, I think this margin is actually smaller than what was reported. Negative discrepancies mean margin was bigger than what was reported. So a negative discrepancy is actually a good thing for the audit, whereas positive is very bad.
Okay.
Alex, do you want to be unmuted again?
I mean, I have, I guess, not much more to add, just to say, I mean, of course, if you just exchange the roles I mean, if you exchange the roles of the tabulated and the actual here, then you would get a positive discrepancy, right? And so then everything you said earlier would be the case. And maybe that's a situation that's a little bit easier to understand, right? That would be a situation where, well, okay, anyway, I guess I don't need to explain, but
Well, and just to finish Alex's question, what you would expect to happen if you keep observing positive discrepancies, what should happen is your audit should say, I can't stop because I've seen too much of an issue. Or it should say, like, I've tried as long as I can, you need to do a full hand recount because I wasn't able to bound the random variable that's discrepancy. I wasn't able to get a good bound on it because I kept seeing these discrepancies as I sampled.
All right.
And Alex and I will be quiet for a second now.
No, that was helpful because this is complicated, but it's almost necessary to understand why the lazy risk limiting method works. Okay, so now what errors could the CVR present? And then the next slide will be about how to fix these errors. So the goal of the check consistent function is to ensure that the audit can be conducted properly with the given CVR, and to check that the CVR and tabulation are consistent with one another, hence the function name and the discussion of discrepancy and CVR and tabulation discrepancy in the previous slides. So check consistent returns an error if the CVR is not formatted properly, identifiers are not unique on the CVR, the batch sizes do not match, and the tabulated vote subtotals do not match the CVR subtotals. The transform function that the auditor can do in basic experiment attempts to fix these errors, and these fixes will be discussed on this next slide. So, the first error I'll address is unique identifiers. So why do we care about them? Without unique identifiers, the untrusted party can respond with different ballots every time an identifier is requested. So if this occurs in the CVR, the fix is that any instance of a repeat identifier after the initial instance of this identifier should be set to no ballot. So the sizes per batch must match. The reason why we care about this is because if the ballot manifest batch size is larger than the CVR batch size, then there could be an instance where a ballot is requested using data from the ballot manifest, and this ballot is not contained in the CVR because the ballot manifest claims there's more ballots than are present in the CVR. So to handle this mismatch, if the batch size is larger on the ballot manifest than the CVR, you add rows onto the CVR that just say no ballot with no vote. Or no ballot, sorry. If the ballot manifest batch size is smaller than the CVR batch size, then you remove the last row of the CVR until the sizes match. The CVR subtotals must match the tabulation. This is the point I've been trying to emphasize in the last few slides. So this check/fix ensures that the discrepancy between the CVR and ballots is the same as the discrepancy between the tabulator and ballots, or tabulation and ballots. So The reason why we care about this is because it forces the untrusted party to commit to a total discrepancy for a batch. It cannot necessarily add more discrepancy to it. So in the event that these subtotals do not match, you want to set the last row of the CVR as a vote for either the winner or the loser, depending on what subtotal mismatches. For example, if there are less votes on the CVR than there should be, then you change the last row of the CVR to be votes for the winner until these two subtotals match. And finally, missing ballots or no ballots are marked for the loser. As I said in unique identifiers section and the sizes per batch must match section, you can change things or add ballots to be no ballot. If when a ballot is requested, either A, it's a no ballot situation, or B, the untrusted party says that no ballot exists, as in they're acting uncooperative with the audit, then this missing ballot should be marked down as a vote for the loser. The reason why we do this is because if we didn't, the untrusted party could choose to not return ballots that show votes for the loser, and this would reduce observed discrepancy. So the good news is, in our paper, we show that these corrections to the CVR do not increase the risk or the chance that a bad election outcome is unnoticed. It may increase the number of rounds you have to do or the number of times you have to check ballots, and it may increase the chance of a full hand recount, but it does not affect the statistical guarantee that RLAs provide. So a few caveats about our method. The first is that only specific statistical tests work due to the adaptive nature of the audit. So an example of a statistical test that does work is the Kaplan-Markov test, which is used for most current risk-limiting audit software. A second one is auditors need some sort of machine in order to produce CVRs. There are currently no individual level CVR producing tabulators, and having a tabulator that pulls and labels ballots is problematic and can raise security concerns over ballot tampering. As I said, any device that can mark a ballot after it's cast could affect the interpretation of the ballot. In Connecticut, we have the audit station, as I mentioned, which we use to create CVRs. We also need, we also do local tabulation, which makes it kind of complicated to get overall tabulation totals. We need better ballot storage in order to easily identify ballots and find specific ballots within a batch. We need a means to identify ballots, which I had that whole conversation about ballot identifiers and putting markings on ballots before and after the ballot is cast. So how do we remedy that? And then finally, there's the question of software. So a question we've kind of sat on since we started researching this topic is, how do you feel confident about the software, and how do you know you can trust software? We've concluded that it's fine if you do not trust software, so long as there's recording proceedings of the RLA that we can use to double check the software's work. The software is mainly responsible for requesting the correct number of ballots, determining if the audit needs to continue in another round, and outputting the final p-value, which is the risk limit. So, conclusions of the method we created. The main advances are that you do batch selected CVRs rather than a large statewide CVR, and we provide formal instructions for how to handle mismatches between the CVR, ballot manifest, tabulation totals, etc. So what does this mean in practice? Batch selected CVRs means that there's cheaper comparison audits for states without CVR producing tabulators. And these formal instructions means there's less ambiguity in discrepancy related decisions. Remember that in normal comparison audits, I said that there's no actual instructions for how to handle any errors or if any of the checks fail. It's kind of up to the audit and audit administrator's discretion. And then, oops, these are the references. So.
Well, I would say let's thank Abby, but I'll clap my hands because I don't know how to do anything else. Yeah, I know it's complicated, but questions from the audience other than me? Alex, you want to ask like a really annoying a question about like a dominated martingale or something?
I also saw that Greg raised his hand.
Oh, sure. Go ahead, Greg. I think I asked you to unmute, so you should be able to talk.
Yeah, I mean, like really silly things. Is bad election sort of an industry term, or is that something that we just
I
use internally?
I think that's something we more use internally. Um, there's a lot more complicated way to call a bad election because essentially a bad election is just that the results that the election showed do
Yeah.
not match the results that we found in the audit. But that's
So
not an industry term.
yeah, so okay, so I would maybe say incorrect election outcome.
Okay.
Does that cover it? Like I like these are such silly things that and yeah, I wasn't so on slide 6, you said that the I want to say adversary, but I forget the word that you use.
I used untrusted party.
The trusted party, right? So you said that they can try to thwart the election at every step of the way, and I might say so. I thought you might be. So I thought you could say every step of the way while remaining undetected,
Okay.
and I was wondering if you were going to mention later that maybe a side effect of doing these risk limiting audits would be to detect some of these untrusted parties. So if there was a tabulator that wasn't functioning properly, you might be able to detect it if it malfunctioned enough, right? If it ended up being detected.
Yeah.
But I don't know if that's something that you want to cover.
No, I think this is a really good point, is that you're likely to catch errors as well as adversarial behavior. Right. Um,
Yeah.
yeah.
That's a great point though. I'll include it.
Actually on this one thing, um, right, that's worth saying at least when you talk to the voting people, um, is these things that you say are trusted. Why do we think we can trust those things? Like, I know there's standard assumptions in the literature, but why do we think we can trust them?
Okay.
On slide 10, if it were me, I would change a lot of issues to significant issues. But again, it's a silly, like, insignificant comment.
Okay. Thank you.
And then I think on line 17, it took me a minute to sort of catch up. Um, and so just maybe in discussion saying that, the, or I guess saying, the actual votes, the real outcome I guess it really explaining the questions that Ben and Alex had. So saying that the true winner of the election was Biden, and